Hello everyone, welcome to Castro in the Classroom. It's great to be here. I'm Christene Lynch and I'm an astronomer at the University of Sydney. So I'll talk a bit about my research later, but what I mean by astronomer is that I use telescopes from all over the world to answer fundamental questions about our universe and all of the things in it. So how the universe formed, how all of the planets and galaxies and stars formed within our universe, and how they all evolved with time. So in the beginning, I'll talk a bit about what I mean by solar system and where we're located in our universe. I'll also give a bit of history on observational astronomy and how we've gone from doing astronomy with our own eyes to using telescopes and satellites. And then I'll talk about how these telescopes and satellites actually helped us to rediscover our solar system, to understand what the different bodies in our solar system look like and what their different properties are. And then lastly, I'll talk a bit about how telescopes make invisible things visible to our own eyes. So just before I get into all that, a brief bit about what I do. So I'm what's called a radio astronomer, and that means that I use radio light to study things in our universe. This is a picture of the Australia Telescope compact array in Narrabri. And I use that telescope to study radio light from the very smallest of stars. So these stars are about 1/10 of the size of our own sun, and they have very energetic flares, very similar to solar flares, but they have about 1,000 times more energy than the most energetic flare of the sun. And it's not understood why these small stars have such energetic flares. And so I use radio telescopes to try to answer that question. Now the middle picture is what my computer looks like on a daily basis. I use a lot of computer code, I write a lot of computer code to do all of my measurements and to analyze all of my images. And I make measurements of how bright the stars are and whether or not the light from the star varies with time. And we can tell different things about the star from those measurements, like if the star is rotating and how fast it's rotating. We can also tell how hot the star is and how much magnetic energy the star has. And we can use those different physical parameters to answer the question about why they have these energetic flares. So what do I mean by solar system? So solar refers to our own sun. So it's a body or a group of bodies that are orbiting our sun due to the sun's gravitational pull. So it includes 8 planets and all of their moons, 2 asteroid belts. There's an asteroid belt between Mars and Jupiter, and then one out past Pluto. And then all of these things are contained inside what's called a heliosphere. And this is the region of space that's influenced by the sun's wind. Now, if you imagine that you're on a different planet in a different galaxy, looking back at our own solar system, what would you see if you used a telescope? If you used a regular amateur astronomer telescope, you'd just probably see a point of light. But if you used a little better telescope, you might resolve that point of light into the actual galaxy, which is pictured here. So that's an artist's interpretation of what our galaxy looks like. And then if you had some of the best telescopes, you might be able to see our own sun within that galaxy. And you would get a sense of where our solar system is within our Milky Way galaxy. And we know that our sun is within a spiral arm of the Milky Way galaxy called Orion, and it's located towards the center of the galaxy. Now, most of astronomy before the telescopes was done using our eyes, and you can actually see a lot of different things using just your eyes. Now, you can imagine going out to where it's very dark, away from city lights, from any sort of man-made source of light, and looking up at the sky. And what you would see is several points of light, bright points of light. And as your eyes got more accustomed to the darkness, you'd see more and more points of light. And you can actually see a few thousand stars with just your eyes. Now, what do you notice about these stars if you keep just staring up at the sky? Well, you might first notice that they're not all the same brightness. Some of them are brighter and some of them are dimmer. And this is telling us something about how far away they are. So the bright stars are the closest objects to us. And the dimmer stars are the ones that are further away from the Earth. Second, you might notice that some of them don't look white. They don't have white light. They have maybe blue light or red light. And this is telling us about the temperature of the star as well as the age. So blue stars are hot and they tend to be really young, and red stars are really old stars and really cold stars. And lastly, you'll notice that the brightest points of light make up different patterns in the sky, and these are the 88 constellations that we know of. In the southern hemisphere, the one that most everyone knows is the Southern Cross, and that's the smallest one of the 88. Now, the ancient Babylonians in 2000 BC did a lot of astronomy with their eyes, and they actually were able to note that there were some stars that had these really irregular patterns in the sky, where the star would move in one direction and then move back in the other direction against the uniform stars that moved all in the same direction. And what they called these stars are wandering stars, and they turned out to be all of the planets in our solar system. So the Babylonians were able to identify all 5 of the visible planets in our solar system using just their eyes. In addition to that, Copernicus also used naked eye observing to develop a model of our solar system that could accurately predict the location of a planet in the sky given a time and a date. There were many other models of the solar system before Copernicus's, but Copernicus's was the first one that could actually accurately predict the location of a planet. And using this model, he argued that all of the planets, including the Earth, had to be orbiting the sun. Previous models had argued that you had to be around the Earth, but as I said, they couldn't explain the motions of the planets using those models. So we actually knew a lot about our solar system just from naked eye observing. We knew where we knew 5 of the planets, where they were located in the sky, and we knew what our solar system generally looked like. But we needed to have telescopes to tell anything more about the solar system or the universe as a whole. So the purpose of a telescope is actually to make things easier to see. So this might mean taking something that you can already see with your eye, but making it bigger and in more detail. Or it might take something that you can't see with your eye and make it visible for you to see and study. Telescopes work by gathering light and then funneling it to your eye. So you can kind of think of a telescope as like a big bucket in the rain. The larger bucket that you have, the more amount of rain you can collect in that bucket. So the larger the telescope you have, the more amount of light you can see, and the more dimmer objects you can see. The first telescopes were refracting telescopes, and they used lenses to actually direct and then funnel the light to your eye. And then it was found out later you could use mirrors to do the exact same thing. And this was really important because making a really big mirror is a lot easier than making a really big lens. And so we were able to make telescopes bigger and bigger and see dimmer and dimmer things. So Galileo was the most famous for using a telescope to do astronomy. He wasn't the first person to do that, and he didn't invent the telescope. He's just the most famous for doing it. In this slide, you can see a picture of Galileo's telescope. It wasn't actually that great a telescope. It only magnified things about 14 times what you can see with your eye. But he was able to see a lot of different features on the solar system planets. So these pictures are 3 different drawings that Galileo did of different solar system objects. For Saturn, he could see that there was something orbiting it, maybe some moons or rings, but he couldn't really tell what it was. For the moon, he was able to actually draw all the craters and show that there was a lot of features on the moon. And then the sun, he also was able to show that there are these sunspots and there's activity on the sun and it's changing. And this is really important because before Galileo, everyone assumed that the solar system bodies were just these perfect spheres that never changed and had perfect surfaces with no features on them. And Galileo, using his telescope, challenged that idea and showed that they do have features and that these features change with time. So since Galileo, telescopes have changed a lot. Mostly they just got bigger. But another really important advancement in technology was the invention of what's called a charged couple device. It's called a CCD, as astronomers call them. And there's a picture of one on this slide. So it's the square with a bunch of different squares. That's the CCD. And that one is for the Kepler Space Telescope, which is orbiting the Earth right now, looking for planets that are orbiting stars other than our sun, so exoplanets, and it's doing a great job at that. And CCDs were really important because they were able to collect all the light that normally you would use your eye to do, you could use a CCD to do, and then they would digitize that light signal and make an image that you could look at on your computer. So this was really important for telescopes because the best places to build a telescope tend to be in the worst places to live, on the tops of volcanoes and mountains, in the middle of deserts and in space. So no longer do we need a person to actually be at the telescope. We could just use a CCD instead and then send that signal back to a nice place to live or a nice place to have your lab and analyze the signal. So that's what, in the middle picture there, is the group from the Voyager team who are looking at the signal sent back from Voyager as it was accelerating out of our solar system. And then the last picture is of New Horizons, which is the satellite sent out to Pluto. And you can see that the top of it has a very large dish. And that's the radio dish that New Horizons uses to send the signal back to Earth that we collect with radio dishes here on Earth. So we've used a lot of different satellites to study our solar system bodies. The three pictured here are the ones that have told us the most about the inner solar system, so all of the rocky planets between the inner asteroid belt and the sun. The planets included in this region are Mercury, Venus, and Mars, and our Earth as well. So the first one, the one closest to our sun, is Mercury. It's the smallest of the planets, but it's slightly larger than our own moon. It has a really dynamic temperature range on its surface because it has no atmosphere. The sun has stripped the planet of its atmosphere. And its surface is a solid rocky surface, but has tons of craters just like our moon. Venus is about the same size as of our Earth. It's sometimes called Earth's twin. But it's not actually that similar to the Earth because it has this really thick atmosphere from all of the different active volcanoes on its surface. And the surface of Venus is actually the hottest for the inner rocky planets, and this is due to the fact that the atmosphere is so thick and made of carbon, and it creates this intense greenhouse effect. Earth, we actually study Earth with satellites, and we look at different weather patterns in the atmosphere. And we know that it's the only planet in our own solar system that has life and liquid water. But we don't know whether or not there are planets in other solar systems in the universe that have these things. And there are groups of astronomers trying to actually determine the answer to that question. Mars is the furthest rocky planet out. It has the highest mountain in the solar system, and it's about 3 times the size of Mount Everest. And it's the only other planet to have the poles covered in ice caps besides our own Earth. And the red color is actually due to oxidation of the metallic rocks on the surface of Mars. So you're actually looking at the rusting of rocky material on Mars when you see that red color. Now, the outer solar system planets, the ice giants and gas giants, have been well studied by 3 different other satellite missions, the 2 Voyager missions and Cassini. Voyager 1 has actually left our solar system and is the first man-made object to leave the solar system, and Voyager 2 is on its way out as well. Cassini is actually orbiting Saturn right now, and they'll eventually crash it into the surface of Saturn to study the surface and upper atmosphere of the planet. So Jupiter, it's the most massive of our solar system planets. It's actually twice the total mass of all the other planets in our solar system. It has this giant red spot, which is a cyclone that's been going on for 300 years, as long as we have observed it. And because it's so massive, it's actually able to collect a lot of things as they go by. So it has a lot of moons, like 67 confirmed moons orbit Jupiter. And it includes the largest moon in our solar system, Ganymede, which is actually larger than Mercury. Saturn is another very large planet. However, it's not very dense. It's the least dense planet in our solar system. And these beautiful rings that we see around Saturn, they're made of ice and dust. And they're very thin, only about 20 kilometers thick, but very wide, 1,300 kilometers in distance. And the yellow you see in the pictures and when you look at it through a telescope is because there's ammonia in the upper atmosphere of this planet. Now Uranus is a strange planet. So if you looked at the Earth, it would be rotating in this way, where the rotation axis is going what we consider the top to the bottom. But Uranus is almost on its side, and it's rotating. So it's very different from all of the other planets in our solar system in this way. And it was thought that the tilt to the planet is due to something running into it as it was forming, and it knocked it off its this other axis that was normal for all the other planets. It also has a lot of moons because it's pretty massive, and it's the first planet that was discovered using a telescope. Neptune is the last of our solar system planets. It's blue because of the methane in its atmosphere, and it was actually discovered using math. So an astronomer used orbital mechanics to actually calculate all of the other orbits in the solar system of all the other planets, and determined that you couldn't explain those orbits unless you had an eighth planet orbiting out past Uranus. And so they calculated what the orbit had to be and then pointed a telescope and discovered Neptune. So it's the first one that was discovered just by pure math and understanding how orbits work. And just a little trivia, it's named after the god of the Roman god of the sea. Now, you might be wondering about Pluto. When I was your age, we had 9 planets, Pluto being one of them. And in 2006, they determined that Pluto wasn't a planet, but a dwarf planet. And we've sent out New Horizons to actually study Pluto, which is this satellite. And using New Horizons and a few satellites between, we've actually been able to resolve features on Pluto in a much better way. So this video is showing you basically the evolution of what Pluto looked like since it was discovered to now. It's quite remarkable how much different it looks from when we first discovered Pluto. It was discovered in 1930 and then, as I said, reclassified. It's the second largest dwarf planet, so there's a dwarf planet actually larger than Pluto orbiting out past Pluto, and its orbit takes over 200 years to complete. Now the last thing I want to talk to you about is how telescopes make light that is invisible to our eyes visible. So we know that light that we can see, if you pass it through a prism, you get a rainbow of colors, just like this picture shows. And the number of different types of light you can get is actually much broader than just what we can see with our eyes. So we can see what's called visible light, and you can see the rainbow of colors in the middle of this plot. But we have light that goes all the way from radio, low energy radio waves, radio light, all the way to high energy waves, gamma rays. And to actually study different astronomical objects using these different types of light, we have to develop different telescopes. So as I said, we can see visible. And earlier I said I was a radio astronomer, and that's the light that I look at. So this is another picture of the Atacama compact array, Australia Telescope compact array, sorry, that I use. So we had to actually build a completely different telescope to study radio waves than we would had to have built to study optical light. And it's the same for looking at gamma rays and X-rays. The telescopes change with what type of light you're actually trying to look at. So that's all I had to present to you today. I'm very happy to be here to talk to you about these things, and thank you so much for listening. Thank you.